Okay, in section 2.5, we're going to continue the work that we've been doing in dealing with finding zeros and solving polynomial equations ultimately. And we're just going to expand our work to being able to work with complex zeros. So they could be real or non-real. The work that we've done so far have been when we only have had real zeros. Okay, now we're going to look at can we have complex zeros, meaning real and non-real. And what it boils down to is there's a fundamental theorem of algebra, okay, which obviously seems like a pretty important theorem since it's got the fundamental to it. Okay, there's also a fundamental theorem of arithmetic that we learned at one point in math. We won't revisit that now, but there's also a fundamental theorem of calculus as well. When you continue on, you'll get to that at some point. But this fundamental theorem of algebra guarantees us that if we have a polynomial function of degree n, okay, that it has n complex zeros. And some of these zeros may be repeated. So we've seen some quadratic functions and linear functions, of course, which we know always have either one or two solutions. Okay? And we've seen some cubics, and sometimes we've gotten only one zero, but we've also broken it down into a quadratic that may have had complex zeros, may have had imaginary ones. Okay? And what this theorem guarantees is that whatever the degree is, okay, there's going to be that many zeros. Okay? So if we have a degree 5, okay, how many answers are we going to be looking for? 5. Okay, if we have degree 100, we'd be trying 100 answers. Luckily, we won't have to do that in this class. But ultimately, that's what we're after. If we have a degree n, okay, then we're going to have always n zeros. Okay. Now, there's a couple of theorems that we're going to look at in this section besides that one as well, and then we'll get into some work here in a second. So this one tells us that if we have a polynomial function of degree n greater than 0, so in other words, if it's linear or quadratic or cubic, etc., then f of x has precisely n linear factors. Okay? And it doesn't really matter what a is here. A could be the leading coefficient. It could be a 1. It could be 5. It could be a -3, whatever it may be. And ultimately, these z1, z2, and so on are going to be the complex zeros of f. Okay? And these z's are not necessarily distinct numbers. Some may be repeated. Okay, we've seen some that factor where we have maybe we have -2, 0, but it's got multiplicity 3. Okay, those count for 3 when we're talking about how many. And so what that theorem essentially tells us is that no matter what the polynomial is like, we can break it down into linear factors. Okay, and how many linear factors? There's going to be n, the same as the number of degree. If there's n zeros, there's going to be n linear factors. Okay, all right. And one more theorem here that is kind of exactly the same as one we saw earlier in section 2.4. So the following statements about a polynomial function are equivalent if k is a complex number. Okay. So again, keep in mind, complex number just indicates that it could be real or it could be non-real. Okay. All real and non-real numbers are complex. Okay. So ultimately, if we have k, that's a solution to the equation f of x equals 0, then we say that k is a 0 of that function, and we also know that x minus k is a factor. Okay, when we did our opener problem today, we found the zeros, and then we changed them into factors, didn't we? Okay. So the theorems that we've learned so far allow us to do exactly that. Okay. All right, so what we're asked to do here in this one is to write a polynomial function in standard form and identify the zeros of the function and the x-intercepts of the graph. So we were given this f of x. It's in factored form, as we can see. So if it's in factored form, that's not standard form. We need to ultimately multiply that out. Okay? So before we do that, though, it says identify the zeros. Well, in this particular case, we can see that the factors are given. So the zeros are just going to be 3i and -3i. So those would be our two zeros, if you will. And then how about the x-intercepts? Before we actually multiply, if these two are the zeros, what are we going to see when we graph this? Will we see any x-intercepts? No. Okay, because if these are imaginary roots, imaginary zeros for this equation, then we're not going to see any x-intercepts here. And we can see that, of course, it's going to be x squared, so it's going to be a parabola. So think about what that's going to look like when we eventually graph this thing. Okay, it's going to be a parabola, and the vertex is going to be above the x-axis because it's going to have a positive leading coefficient, meaning it opens up. Okay, And let's see what happens when we do this, because it might be something that we can actually graph. Of course, when you take your calculator and you put your y equals, you're not going to be able to type in 3i as one of the coefficients. So unless this has real coefficients, then we won't be able to actually graph it with the calculator. So if we do the FOIL method here, if we do x squared plus 3ix minus 3ix, conveniently the 2 will cancel out, and we're going to have minus 9i squared. So when we do that, we're going to have these two in the middle cancel. And then when we have 9i squared, remember what I squared is. I squared is actually negative 1. It's the square root of I, or the square root of 1. Negative 1 is I. So if we square that, we'd get negative 1. And so really we'd get down to this would be x squared plus 9. Okay? And so this equation shouldn't be terribly surprising, because all it is the x squared function moved up 9. Which means that the vertex is above the x-axis and it opens up, so therefore there would be no real zeros, therefore no x-intercepts. Fair enough? Okay. And again, of course, we could graph that either by hand or by calculator and show that that's a fact as well. Okay. All right. Okay. Now, you'll notice in that particular case we had I and 3i and negative 3i as our two zeros. Okay, that's not an accident. What it boils down to is, this is kind of an important theorem as well. When we have any polynomial function that has real coefficients, and this is a key, it's got to have real coefficients. Okay, we can't have one of the coefficients be 3i or something like that. Okay, ultimately, if we have real coefficients, okay, and a and b are real numbers, b not equal to 0, then a plus bi is a 0 of x. Then its complex conjugate, a minus bi, is also a 0. Okay. So ultimately what that says is that when we have non-real zeros, that they come in pairs. Okay. So notice the last time we had 0 plus 3i, okay, the other 0 is 0 minus 3i. Fair enough? Okay, if I put it in that a plus bi form, or a minus bi form. So if this is a 0, then so is its complex conjugate, which is just the same exact number, but with the opposite sign in between. Alright, so with that said, here's another problem that we're going to look at here. It says write a polynomial function of minimum degree in standard form with real coefficients whose zeros include these three. Now, I want to do a couple of things here with the algebra on this to make sure that we're clear on what to do. First of all, the real zero here that we have, we can write as x plus 3, so x minus negative 3 if you will. Okay, but then if we have 3 minus I as a 0, okay, when we write that, we're going to write x minus 3 minus I. But by having 3 minus I here, okay, what else is a 0 based on that last theorem that we looked at? 3 plus I is also a 0, so we'd write x minus 3 plus I. Okay. And then again, we'd write x minus 2 plus 5i. But what else would be a 0 if 2 plus 5i is? X minus 2 minus 5i. And those would be the 5 zeros that we would get in this case. Now, if this statement didn't say real coefficients, okay, then we wouldn't need those other two. Okay, we would have left this one and this one out. Okay? But since we had to have real coefficients, we know that any non-real 0 is going to occur in a conjugate pair. Okay? So even though they only gave us 3 zeros, this really had to have come from a 5th degree equation because of that real coefficient stipulation. Okay? So again, that's key that we want to look for, that we're writing this with real coefficients. Okay? Now if you forgot that and you left those two out and you just started multiplying, when you got done, would you have real coefficients? Nope. Okay? What's going to happen here ultimately is that when we do all this multiplication here, which we're going to in a minute, okay, all those i's are going to be gone when we get done. So that's good news, right? Okay. Alright, so let's see how we're going to handle this algebraically. What's the algebra going to look like when we do this multiplication? Here's my advice to you, is I would not multiply these two together first. Okay, I would always multiply the conjugate pairs together first. Okay, so we'll do these two, and we'll do these two. Because if we're lucky, when we do these two and these two, we're going to have the i's be gone already. Okay, that's our hope. So let's find out. Now, there's one other thing that I would do as well, is that when I see this situation, when I have x minus, and then the 0 is a binomial, if you will, okay, I'm going to rewrite that as x minus 3 plus I. And this one, x minus 3 minus I. Okay. I'm going to actually distribute that negative into the parentheses. Okay, and then I'm going to multiply these two as if they're trinomials. Okay, so that's going to be your best case scenario to get this right. So we're going to write minus 3 minus minus is going to make a plus I in that one, and then a minus and a minus. And that's going to be what our distributed part looks like. So let's start with the x. If we do x times x, that's x squared. If we do x times negative 3, that's negative 3x. If we do x times negative I, we're going to get negative ix. And then we'll do the negative 3 right here. Negative 3 times x is negative 3x again. Negative 3 times negative 3 is plus 9. Negative 3 times negative I is plus 3i. Okay. And then finally we'll do the I term. The I times the x is going to be plus ix. I times negative 3 is going to be negative 3i. And then I times negative I is going to be minus I squared. Okay. So those would be the 9 terms that we get in this case. And if we look at what happens to our different parts here, we have an x squared, of course. We have negative 3x and negative 3x. That makes negative 6x. And notice here we have a negative ix and a positive ix. So those are gone. We have a 3i and a negative 3i. Those are gone. Okay. We do have a plus 9 here also. Okay. However, we also have a minus I squared. This is really minus negative 1 then, isn't it? Okay. So with that said, we combine the 9 and the negative negative 1 and we get plus 10. Okay. And so that right there would be the quadratic equation that would have those two factors, okay, which ultimately would have those two roots that we made the factors from. Alright, and then if we do the same thing with the last two, I'm going to again rewrite those as x minus 2 minus 5i, and then x minus 2 plus 5i. So I'm going to distribute the negative, make them trinomials. Okay. And then from there, I'm going to go ahead and multiply those out, same way as I did the last one, and see what we get. So we're going to do x times x times negative 2, x times 5i. Then we'll deal with the negative 2. So negative 2 times x, negative 2 times negative 2, negative 2 times 5i is going to be minus 10i. And then finally the negative 5i, negative 5ix, plus 10i. And then here we're going to be minus 25i squared. Alright, so we'll get our 9 terms by doing that multiplication. And then we'll have x squared minus 4x. What happens to the ix's? The ix's are opposites, so those are gone. The 10i and the negative 10i are opposites, so those are gone. And then we have a 4 here, but what do we really have here? We have minus negative 25, essentially. So really it's plus 25. So we'd have a 29 on the end. And we'd have x squared minus 4x minus 29. Questions so far? Alright, so almost there. So now the best case scenario is to do these two next to each other. Remember, these would be the two quadratics that we made from the linear factors that we had. So if we had x squared minus 6x plus 10, and then x squared minus 4x plus 29. Okay, let's go ahead and see what we get here. So x squared times x squared, x to the 4th. X squared times negative 4x would be minus 4x cubed. X squared times 29 would be 29x squared. We'll do the same thing with the negative 6. So it would be negative 6x cubed. And then plus 24x squared. And then 6 times 29 would be 174. X, of course. And then the 10, we're going to have plus 10x squared minus 40x. And then plus 290. Okay. And from there, combine the like terms, and we'll get down to x to the 4th. And we have minus 10x cubed. Got 29 and 24, that would make 53x squared. Oops, I forgot about my 10 there. It's actually 63x squared. Okay. And then the x's, we'd have negative 214x plus 290. Alright, now almost there. Still have one more factor though. Remember we had an x plus 3 out in front at the beginning. So once we multiply that by x plus 3, then we're going to be good to go. So let's go ahead and do that with the x. We're going to have x to the 5th minus 10 x to the 4th plus 63 x to the 3rd minus 214 x squared plus 290x. X times each of those. And then if we do 3 times each of those, we're going to get 3x to the 4th minus 30x cubed plus 189 x squared minus 642x and plus 290 times 3 would be 570. Okay. And then from there we combine like terms and we'd be done. Okay. All right, and keep in mind if we had to do that backwards, in other words, being given this 5th degree equation, okay, we let's see, 14 plus 20 minus 25x squared, and this would be minus 352x plus 570. Okay. We would still look at factors of 570 if we were to do this in the reverse order. 570's factors we could make a list of. We could start dividing. Ultimately, we would end up finding -3 as a solution, wouldn't we? Okay. Now, think about it though. If I had that left over as my quartic equation, okay, would I be able to really do anything with that? If I tried to take 290 and find more rational answers from it, I wouldn't find any, would I? Matter of fact, when I graphed this equation, I would only see one x-intercept, wouldn't I? So if it was a 5th degree equation and I could only see one intercept, would there be any way that I could start with this and get back to what I just finished? Okay, no. The only way that you could do that really at this point is by using the quartic formula. You know, we have a quadratic formula. Okay, there is a cubic formula and there's a quartic formula, but they're both very, very complicated, and we won't actually do that in this class. Okay, but that would really be the only way that we could get those particular zeros.